Okay, so this is chapter 4, section 7, and what we're going to talk about is inverse functions. And something to keep in mind is what is an inverse, what is a reciprocal, and I don't want you to get those two things confused. So let's take some notes on that. Okay, so here are some things I want you to keep in mind. An inverse is where your x and y coordinates have been inverted. So for instance, what I'm referring to is, let's say I have the point 1, 2. The inverse of that point is going to be 2, 1. So we took all of our x's and our y's and we swapped those. For a reciprocal, it's the opposite of a given function. So let's say 2. I'm going to flip that over. If you want, you can put that as 2 over 1. You flip it over, the reciprocal is a half. So an inverse is clearly not a reciprocal. And remember, when we're evaluating the trig functions, God bless you, let's say y equals the sine of x. Remember that your input is the angle, and the output is the point on the unit circle. All right, so when we're evaluating y equals the sine of x, the input x is the angle on the unit circle. So if we're talking about pi over 4, pi over 2, pi, and then I want to know the corresponding point on the unit circle. The y is the output, is the point on the unit circle. So if I'm inverting that relationship, if I'm finding the inverse, now I'm reorienting this. So now I'm taking x equals the sine of y. That's going to be the inverse of that sine. So now notice that our input y is the point on the unit circle, and our output is going to be the angle. So when we're looking for the inverse of sine or cosine, tangent, cotangent, what we're looking for is the angles. All right, so I had you guys remember 3 points that are repetitive on the unit circle. One of them was pi over 4. That corresponded to root 2 over 2, root 2 over 2. The other one was pi over 3, which corresponded to 1/2 root 3 over 2. The other one was pi over 6, which corresponded to root 3 over 2, 1/2. And remember that x corresponds to cosine, and that all the y's correspond to the sine when we were evaluating for the angles, and then we were looking for the point on the unit circle. Okay, so remember when we do inverse notation, we use the symbol. So if I was asking you for the inverse sine of pi over 3, what I'm asking you is, what is the corresponding point on the unit circle? And that answer is going to be root 3 over 2. And that's what we're looking at. However, there's something else I want to add to this. If we're graphing the graph of sine, so let's create a quick graph of the graph of sine. And let's just do one cycle. I think one cycle is sufficient. So 0, pi over 2, pi, 3 pi over 2, 2 pi. And the sine curve looks like this, goes like this indefinitely to the right, starts creating these peaks and drops. It clearly passes the vertical line test. That means that it is a function itself. However, when I do the horizontal line test, it does not pass the horizontal line test. You're intersecting it at more than one point. And remember, the vertical line test or the horizontal line test states that it is not a function if it intersects more than once. Specifically, the vertical line test is the function itself. The horizontal line test tests to see if the inverse will be a function. So the inverse of sine is not a function. So in order for the inverse to be a function, we need to restrict the domain. So let's restrict the domain so that the inverse will be a function. If the domain to say negative pi over 2 and positive pi over 2, then the inverse will be a function. Here's negative 1, here's 1. Remember, your function starts here at 0, then it peaks. That's all we want. If I'm going in a negative rotation, okay, it's not pretty, but we're going to pretend that's our restricted sine function. Does it pass the horizontal line test now if I limit the domain? The answer is yes. It's only intersecting at one point. So the inverse sine function, remember, it's denoted by this symbol, and that does not mean flip over sign to get 1 over the sine of x or cosecant. This is inverse notation. Is the inverse of the restricted sign function. We need to restrict it again from negative pi over 2 to pi over 2. And this is again is rad y equals the inverse sine of x. Here is another graphical representation. It's prettier than my drawings. If I'm looking over here, you can clearly see that the parent graph, y equals the sine of x, does not pass the horizontal line test. It's intersecting multiple times. So that means the inverse is not a function. So what do? We restrict it. This is a nicer restricted graph between negative pi over 2 and pi over 2. We know if we're looking at the unit circle, here's 0, here's pi over 2, here's negative pi over 2. So what we're saying is that the inverse sign only is existing in these two quadrants, in a quarter of a positive rotation and a quarter of a negative rotation. So inverse sign only exists in quadrants 1 and quadrants 4, specifically from 0 to pi over 2 and 0 to negative pi over 2. Okay, so quick study tips, everything that I've been saying thus far. If no horizontal line intersects the graph of function more than once, the function is 1 to 1 and the inverse is a function. We did that horizontal line test. The sine graph is not a 1 to 1 function, so we have to restrict the graph. If the point AB is on the graph, then the point BA is on the inverse graph. And again, notation information, that's really important. If it's written like this, y equals the inverse sine of x, that does not mean y equals 1 over the sine of x. This is what I was talking about before. Y equals 1 over the sine of x is equivalent to the negative 1 being outside of sine of x. That means y equals cosecant. So don't confuse a reciprocal and an inverse. Those two things are very, very different. Inverse function means we took the x, the y's, and we switched them. Reciprocal means I flipped over the fraction. Okay, here's a function in its inverse. Here is the restricted sign graph from negative pi over 2 to pi over 2. We can see that our range is from negative 1 to 1. Here is the inverse function where we took all the x's, all the y's, we flipped them. So now our input is the point on the unit circle. Our output is the angle. And here are both of them graphed on the same coordinate plane. And you can see that they're reflections over the line y equals x. Why? Because you took all the x's, the y's, and you flipped them. Okay. What we're looking for is, okay, here's our input, here's our angle. Here's our output, here's the point on the unit circle, but now we're going to reorient it. Our input now is the point on the unit circle, and we're going to look for which of these angles is part of the solution. Okay, so let's start taking a look at some examples. Again, remember, we're going strictly from negative pi over 2 to pi over 2. So if you give me anything greater than pi over 2 or anything less than negative pi over 2, you're doing something wrong. Take a look at the first example. We're finding the exact value of inverse sine of 0. So now this 0 represents the point on the unit circle. I want to know which angle does this happen at. It happens at, look back at that table, it happens at 0. If we look at question B, it says find the exact value of arc sine negative 1. This is just another way of writing inverse sine. So if you ever see me or hear me write or say arc sine negative 1, I'm referring to the same concept, inverse sine. Remember, negative 1 refers to the point on the unit circle. I want to know which angle gives me an output of negative 1, but specifically on the interval of negative pi over 2 to pi over 2. Don't give me anything else other than that. And negative 1 is at negative pi over 2. We know that sine has multiple outputs at negative 1, but again, arc sine, inverse sine, only exists from negative pi over 2 to pi over 2. So here, there's only one solution. Let's take a look at the third one. The third one says find the exact value of inverse sine negative root 3 over 2. So this is the point on the unit circle. And now we identify the angle between negative pi over 2 and pi over 2. Where does this happen at? Negative pi over 3. One solution. Now let's explore the graph of y equals cosine of x. Again, your input is the point on the unit circle. Your output is I said that backwards. Your input is the angle, your output is the point on the unit circle. So let's take a look at a quick graph of y equals cosine of x. Remember your amplitude -1 to 1. And let's do those 5 key points: 0, pi over 2 pi, 3 pi over 2, 2 pi. Okay, cosine starts at the point of displacement. And here is a quick representation of one period of cosine graph. We can clearly see that it does pass the vertical line test, but it does not pass the horizontal line test. So the inverse has to be restricted. If I restrict the graph to, say, just this region here and this region here, this piece of the graph, 0 to pi, will pass the horizontal line test. And that is exactly where the graph of inverse cosine is restricted. So restricted, again, we're going to restrict it from 0 to pi. Here's the graph from 0 to pi. Then it passes the horizontal line test, so the inverse will be a function. And here's the inverse graph. It passes the horizontal and vertical line test. So from 0 to pi, that's in quadrants 1 and 2. So this is different than the graph of, remember, here's 0, here's pi over 2, here's pi, here's 3 pi over 2, and then 0, we're back at 2 pi. So 0 to pi would be this rotation for quadrantal angles. So my solutions now for arc cosine or inverse cosine are strictly going to be in quadrants 1 and quadrants 2, because we restricted the domain in order for the inverse of cosine, in order for the inverse to be a function. So from 0 to pi, we have an inverse. Yeah, inverse cosine, again from 0 to pi. These are the angles. Oh, I didn't mean to do that. I meant to point. So from 0 to pi, it's going to be those angles that we're looking for, and these are the points that we're going to be evaluating. So let's take a look at an example. Again, if you see me write or say arc cosine, that's just another way of saying inverse cosine. We're evaluating inverse cosine now at 1. So remember, this is the point on the unit circle. We're looking for the corresponding angle. So where is arc cosine 1? Which angle does that happen at? 0. And remember, it has to be between 0 and pi. Yes, the graph of cosine at 2 pi does equal 0, but that's outside of the domain and range for arc cosine. So I have to make sure that I stay in the interval from 0 to pi. Arc cosine at root 2 over 2. So what angle does cosine equal root 2 over 2? That's what we're asking here. Pi over 4. And next one, arc cosine at root 3 over 2. What is the solution here? Good. Okay, pi over 6. When you're using a calculator to evaluate these inverse trig functions, you want to make sure your calculator is in radians for what we're going to be doing. If you have a scientific calculator, you have to enter the measure first and then hit second sign. If you have a graphing calculator, it's easier. You just hit second sign. Remember, that brings up the sign to -1 button, or inverse sign, or inverse cosine, whatever we're evaluating. Then you put in the measure, the whatever's given to you, and then you're looking for the angle in radians. Round to about 4 place values. So let's take a look at an example. Okay, use a calculator to find the value of 4 decimal places for each function. Again, make sure that you're in radians first. So we're going to hit inverse tan -5.2. To 4 place values, the solution for the first one is approximately -1.3808. Okay, now let's find inverse cosine at 0.2. And the solution for B is approximately 1.3694. Let's find arc sine or inverse sine at 0.8. Here the solution is 0.9273.